right now machine learning, and this is because this is preliminary to the use of machine learning, because you have to describe features in some way associated to protein structures, okay?
Right, yes.
And usually features are related to distance contact maps and things like that. And the idea is to substitute this kind of presentation of translation, let's say, of the structure with this kind of stuff, which and I still have to find a way to fit a neural network with this stuff, but I think it's possible. It's just a matter of
you might test with other algorithm and find the best one. Probably say there's something which could be best. Okay, and thank you for the answer. And there's one last question, that in the conclusion you said that it is best suitable for the two-dimensional, the 2D structure. So like, do you have any plan to address the same thing in 3D? Because you said
of course, in principle, I have plans in the future, but I'm still working on 2D structure.
Okay.
But okay, of course, my idea is to progress as much as possible. So,
thank you. Yeah, perfect, and all the best for your work.
Thank you.
Thank you again, Andrea.
We can move to the next speaker, Gwinda. Abbiamo il programma qua. Aspetta, che mi sa, lei lo aveva scaricato. Qui. Okay, the next speaker is Gwinda Eka Pratiwi from the Institute Technology Bandung, and she will speak about the electrochemical thermodynamics properties screening of a very large molecule with the metal complexes with extended thick binding quantum chemical method. Please, Gwinda.
Okay, good afternoon, everyone. I'm Linda from Indonesia. So this is my presentation. I'm going to present about the title, and the title is Electronic Chemical Thermodynamic Properties Screening of Many Complexes in Metal Complexes with an Extended Type Binding Quantum Chemical Method. And this is the
It doesn't work. Okay. No, it can't move.
No.
You need to move from the. If you need the last. Okay. You.
So you have to just use
The first. Okay. Can you? No. This. Scroll. No.
Oh, it's okay.
Okay. No, it was switch off. It was switch off.
Okay.
Spin.
Oh,
Switch off.
Okay. Okay, this is the overview in this presentation. The first is introduction and methodology and result and discussion. So the result and discussion consists of stabilization of complex compound with various metal complexes and effect of ammonia ligand on the stability of the complex. And then the third is effect of electron distributions on the stability of the complex compound, and the fourth is global reactivity descriptor, and then the last is frontier molecular orbital. So this is the overview, my introduction. This is the metals, transition metals that this research: chromium, mangan, ferrous, cobalt, and nickel. And then if the coordinate with the base ligand, so they have potential medical fields like antibacterial, anti-cancer, and antioxidant. So the support research for this research is the coordination of shift-based ligand with the transitions metal can be potential, and this more attention for the researcher to develop with the many applications in the biological and medical applications. So this one of the shift-based ligands, especially in hydrogen. Hydrogen in one of the shift-based compounds, especially in azomethyl groups. So this is a double bond carbon with the nitrogen. This is the point of the substantial for biological applications. So the next is shift-based complex ligand with the transitions metal have been synthesized and successfully complex the useful to fill of antimicrobial. And then this research with used to GVN XTB method in competence studies, and the difference to XTB is more advantage like such as fast calculations, and then they have a high accuracy for geometry molecular and then frequencies, especially in organometallic and then complex compound. So this is the point of the introduction or motivation why this research the research can be worked. The first is potential first role. Transmission metal in the medical field is more like a potential to coordinate with the basic ligand, especially its azometic. So the second is shift-based complex. Shift-based complex important and then common to research about the medical field like antibacterial, antioxidant, anti-cancer, and etc. So this research about FDPH and SDP is complex. So this is my research. FDPH is phenylene dinitrophenylhydrazine and SDPH is salicylhydrazine 2.4 dinitrophenylhydrazine. So we use the GVN to XTB method because this is the popular computational science in chemistry. Okay, this is the methodology that we use. So this is GVN XTB have been developed in the many chemistry field, like because this is they have accuracy optimization of this structure, especially in platinum-3 complex compound, and then the GVN XTB have developed because it has a good geometry. It has the result of the GVN XTB can have the good geometry optimizations, and then it can test benchmarks set regarding. And then this methodology used so many complexes, or maybe tens or 100 complexes that we use. We all calculation with ORCA 4.0, and then we use Avogadro software and chemical software, and we use standard temperature and pressure. So this is the standard temperature and pressure. So after that, we calculate optimizations geometry, and then after that, we use calculations frequencies to analyze many properties like electronic, chemical, and thermodynamic to screening of all complex if high stability, so they can be successful in experiment. So we should be know about the importance of condition to successful in experiment. So this is the methodology. We prepare the input of ORCA and then with Avogadro software and etc. And then this is this SDH complex, FDH complex. And after that, we use electron properties, chemical properties, and then thermodynamic properties. So the result and discussion of this research is the first is establishment of a complex compound. This is the graph of the result. This is the X coordinate transition metals, chromium, mangan, ferro, cobalt, and nickel. And this is the delta G or free energy gives. And then this is the any complexes. So the data result can complex with the chart 3 has a more stable with than the complex with the three two plus. So the complex with the FDPH ligand have a more stable than the SDPH complex compound. So after that, we analyze the effect of ammonia ligand. So many complexes shows that complex with additional ammonia ligand has more stable with none or without additional ammonia, because ammonia is base ligand that strengthen H2H or water. So they can be formed to stabilize the system or metals and coordinate with the ligands. So the ammonia ligand has a more stable with additional in complexes. So it is the effect of electron distribution. Electron distribution is like a low spin and high spin. And then this is the metals, the complex with the low spin that have highest negative group gives free energy. It can indicate for the complex, they can more stable with the other complexes, especially high spin and low spin. So the low spin is more stable than high spin. This is the molecular formula ABCD. So we can use the symbol ABC. And then this is the result of global reactive descriptor. Why we can use global reactive descriptor? Because this is the support of result my research. Because if we know about the reactivity about this complex, we know the experimental is successful or not. So this is the result. One is the first in chemical potential. So the lowest value of the chemical potential has more stable in the complex. So the lowest value of the chemical potential is molecular formula in A, or M3 SDPH2 SDPH2 O plus 1. So this is the molecular formula. And then the next is the chemical hardness and the softness. Why we can analyze the chemical hardness and softness? Because this is connecting to reactivity of the complex. And then the conclude of this data is high hardness complexes have tendency or indicate the stabilization of the system or the complex. So in this research can conclude the any complexes have a hardness, not softness complex. So many complex have a more stable and then maybe indicate the successful in experiment. So, and this is the softness of the complexes. The data result is show the most significant softness. The stability of the complex compound will decrease, and then it can be reactivity of the complex. So this is the electronegativity. But in this complex, any other complex have a same value of electronegativity. And then the global electrophilicity. In this research shows that electrophilicity of any complex in here shows the capability to accept electron. So any complex is not nucleophilic but indicate the electrophilic. And then this is the frontier molecular orbital or FMO. FMO based on homo-LUMO gap energy. We can analyze homo-LUMO energy and then we can conclude the frontier molecular orbital like that. So the graph shows that any complex that have a stabilized or stable in many conditions. And then any ligand can have energy gap different SDPH, FDPH, and ammonia and water. So the highest value of homologal gap is the ligand of ammonia. So this is the connecting about the ammonia in additional ammonia can make the system or the complex to stabilize or stable. So this is the conclusion of the results. The first is SDPH and FDPH complex have the stable and then the spontaneous condition. So with the FDPH complex are more stable than the SDPH complex. And then the third is complex with charge 3 plus is more stable than the complex with charge 2 plus. And then the next is electron distribution with the low spin. Result is a more negative Gibbs free energy than the highest spin energy. And the next is the ammonia ligand have a more stable with this complex, not without the ammonia ligand. So the last of conclusions, the acquired result are supported by analysis of global reactivity descriptor like chemical potential, hardness and softness, and then frontier molecular orbital, global descriptor, and etc. So that's all for my presentation. Thank you for LPP to sponsorship my research. Thank you.
Thank you. Thank you, Winda, for this nice talk. Now the talk is open to discussion. Some question here in the audience. I don't know if. Yes, please.
Presentation. I noticed that your plots are show usually.
La siguiente, the next is there.
Some progress.
The next presentation is there.
Like
Yeah.
jumps corresponding to
Yes.
So for example, there is one case, this one of the last slides shows you go back just. No? One.
So yes.
See, it's how could you there is a possible explanation for that?
Yes, because any properties and characterization of the transition metal is different. So many, maybe any anomaly value or energy for these, especially in cobalt complexes like that. So why the value or graph in not really good like that? Because in computational studies, maybe any error or any different energy from any other theory.
Okay.
Thank you.
Thank you.
Some questions at home?
No.
No, any questions? Thank you very much again. We move to the next speaker, Marcio Rossi from University of Perugia, and he will speak about the formation routes of CO from O plus toluene, a computational study.
Sorry to interrupt. We don't hear you online, please.
Continuate a non sentire?
Adesso sì.
Adesso sentite? Ah, la chiavetta, vabbè. Sì.
Now it works, okay. We can continue. Okay. Problem solved. We can restart with presentation. Martin, I don't know if you are in introduction or...
Okay, it seems that there is an interference with the pointer, so I will go on without pointer. So I was just saying that the reaction of oxygen in its triplet p ground state and first excited 1D state are very relevant both in combustion and in atmospheric chemistry. For this reason, we perform experimental and theoretical investigation of these reactions in order to understand their dynamics. So first of all, we perform cross-molecular beam experiments with the soft electroionization mass spectrometric detection in terms of light analysis in order to understand which are the main products of these reactions and their relative branching fractions. Then we perform high-level electronic structural calculation on both of the triplet and the singlet surfaces, and followed by statistical RRKM mass equation computations of product distribution as a function of the collision energy. The cross molecular beam technique allows us to study reactions under single collision conditions. This technique indeed offers the possibility of watching atoms and molecules while they are reacting from measurements of angular and velocity distribution of reaction products. So this is the scheme we generally follow when we perform our investigation. First of all, we consider the experiment, which can provide information, the dynamics of these elementary reactions, and can provide, of course, information on the primary products and branching fractions. Then, through ab initio calculations, we study the potential energy surfaces of the systems under investigation, and through statistical RKM mass equation calculations, we got information on the branching fraction, so we can compare also the experiment with theory. Then we can perform kinetic calculations, computing the rate coefficient as a function of temperature and pressure, and so we can use all this information for the kinetic modeling of different systems important combustion, plasma, atmosphere, or astrochemistry. In particular, the reaction between oxygen and toluene, which has been studied experimentally at a collision energy of 8.3 kilocalories per mole, is found to lead to the formation of phenoxy as a main product channel, followed by the formation of the methyl phenoxy. That is the elimination of methyl in the first case and hydrogen in the second case. For the triplet surface, the channel leading to methyl cyclopentadiene and carbon monoxide is negligible, as it was supposed. But this this channel should be relevant for in the singlet surface, that is for the reaction between oxygen in its first excited singlet D state and toluene. In order to get theoretical information on this system, we perform density functional calculation using the omega B97XD functional with a split valence basis set. And at this level calculations, we perform geometry optimization and localization of transition states. We check the nature of the stationary points, performing, of course, the frequency calculations, and we assign the transition states to the correct reaction, performing intrinsic reaction coordinate calculations. Then we refine the energies, performing couple cluster, single, double, and triple excitations, using a larger basis set that is triple zeta plus polarization plus diffuse function basis set. Let's consider the results of our study. As far as the triplet surface, that is the reaction between oxygen in its ground state and toluene, as a first step we have the formation of Van der Waals adduct, slightly more stable than the reactants. Of course, we can have 4 different isomers depending on the site of attack of the oxygen to the toluene ring. So we can have an attack in ipso, in ortho, in meta, and in para. These Van der Waals adducts can evolve through a transition state to a minimum which is around 11, 12 kilocalories per mole more stable than the reactants. Again, we have 4 different isomers. These species then can lead to hydrogen or methyl elimination depending on the initial site of attack of the oxygen to the toluene ring. If the attack is in ipso, we have elimination of methyl, but in order to get these reactions, it's necessary to overcome initial barrier slightly over the energy of the reactants. The isomers where the attack of oxygen is in ortho, meta, and para, of course, can lead to hydrogen elimination. And also in this case, we have it is necessary to overcome a barrier, an energy barrier higher than the reactants, and in the preferred reaction seems to be the one where the oxygen is bound in the ortho site. The reactions of oxygen in the first excited states, 1D and toluene, that is the reaction which happens in the singlet surface, is completely different because the oxygen in this case can bound to 2 adjacent carbon of the toluene ring. This is because the oxygen in this case has 2 ampere electrons with different spin, which can interact each one with the electrons involved in the carbon-carbon pi bond of the toluene ring. So in this case, we can have only 3 different isomers depending on the sites of attack of oxygen to the ring. In this case, here I have reported the relative energies of these isomers with respect to the most stable isomer, which is the first one. These species can then evolve, giving rise to the products, and the first step of the reactions is always shift of an hydrogen from one carbon to the adjacent one. Also in this surface, in the singlet surface, we can have elimination of hydrogen or methyl. In this case, I have reported only the first isomer, which is with respect to oxygen triplet P and toluene is 55.4 kilocalories per mole more stable. We can see that we can have the elimination of methyl or hydrogen after initial isomerization of the species. We have also the formation of other species. We have other exit channels, like the one leading to the elimination of water or the one leading to the elimination of molecular hydrogen. But these channels are not really important because we have relatively high barriers and many isomerization steps necessary to arrive to the product. Much more important is the formation of carbon monoxide. In this case, we have 6 different exit channels. Here I have reported the exit channels involved in the isomer 1 and partly the isomer 2, and we have the reaction path in different colors, blue, green, and red. And here I have reported the other 3 reaction paths, starting from isomer 2 or 3, again with different colors. Of course, we can have some information about which one can be the main exit channel, considering the barrier, the energy barriers involved in these isomerization steps. For instance, this path should be relatively difficult because we have barrier much higher than those implied in the other isomerization pathways. So we can have some information from the age of the barriers and also from the number of different isomerization steps necessary to arrive to the products. But in order to have a quantitative information, it's necessary to compute, of course, the branching fractions. We have information from the experiments. This should be the branching fractions which can deduce from the experiments, and we can see that in the triplet surface we have only 2 possible exit channels, the one leading to methyl and the one leading to hydrogen, which is less important, while in the singlet surface we have 3 different exit channels, with the one leading to carbon monoxide being the second one in importance. So to complete this study, now it's necessary to compute the theoretical branching fractions and the rate constant, taking into account, of course, also the intersystem crossing, which should be the main way to arrive to the singlet surface. I would like to acknowledge the Italian MIO for financial support, the University of Perugia, and all of you for your kind attention.
Thank you, Marzio, for this nice presentation and for the inconvenience. And so now some questions for the audience. Please, Winda. No, maybe
please
it's
come.
better that yes.
I want to ask you why you use the toluene. Is it possible to use any solvent, maybe like acetone or anything else?
We are interested in the reactions of oxygen with, in general, with hydrocarbons, yes, because we are considering combustion reactions. We already studied smaller hydrocarbons like butadiene, for instance, propene, benzene. Now we are studying toluene because we are interested also in aromatic hydrocarbons, which are present, for instance, in gasoline. And so the choice is due to the relevance of these compounds mainly in combustion chemistry.
Okay, thank you.
You're welcome. Some more questions at home from the virtual participants? Okay, thank you again, Marzio. Okay, we move, we move to the last speaker, Luca from University of Perugia, and he is virtual. Hi, Luca.
Hello.
Hello. So you can hear us?
Yes.
Okay. Try to share.
Okay. Just a moment. Okay, can you see?
Not yet.
Okay. Now?
Not yet. It's not arriving nothing.
But you don't see neither me?
No, I see you.
Okay.
We are seeing you in the screen, but not the presentation. It's not arriving.
Okay, just a moment.
Yes, yes.
Okay.
Okay, return.
Can you see my screen now?
Yeah, now, yeah, perfect.
Okay. Great, sorry for the inconvenience. So, in principle, now you should see the presentation.
Yeah, can you move to the second slide only to check if it's okay? Okay, perfect.
Okay.
Okay, so Luca, we will speak about the reaction. The sulfur plus silicium hydrogen reaction toward the synthesis of interstellar silicium, the cis reaction. Please, Luca.
Okay, thank you for having me. Today I will try to focus my talk on possible formation mechanism for interstellar silicon sulfide in different regions of the interstellar medium, starting from gas phase ion neutral reactions. So silicon is the seventh most abundant element in the interstellar medium, and its presence is mainly related to the so-called dust grains, which are sub-micrometer side particle with an inner core made indeed of silicates mainly, or in alternative made of amorphous carbon, depending on their origin. Covered by the so-called icy mantles, in which different species and molecules can be trapped, and this mantle can act as a catalyst, catalytic site for the formation of different species. Together with the presence of silicon as silicates in the core of the dust grains, different molecules containing silicon has been detected also in the gas phase in the interstellar medium. In particular, two most important molecules are SiO and SiS, and their presence is mostly related to shock regions, which are regions of the interstellar medium, which is basically the space between the stars, which is made of gas and dust. But shock regions are regions in which the high energetic material ejected by a new formed protostar, which is extremely active, impact a quiescent zone of the interstellar medium, leading to the formation of different processes, including the sputtering of the grains, which allow to release in the gas phase different species, but also gives enough energy to the molecule in gas phase to react and form more complex molecules. Among the different shock regions, one peculiar example is the L1157b1 region, which is a shock region driven by a sun-like protostar, and it's particularly important because the protostar that drives the shock can share some similarities with the first stages of the formation of our sun and as a consequence of our solar system. In particular, a work of 2017 performed by Linda Polio and co-workers revealed the presence of two silicon-bearing molecules, SiO with different isomers, and for the first time, silicon sulfide, SiS. And the main aim of this work is that the two species present a different spatial distribution. In particular, SiO peaks where the jet impact the cavity, while SiS is present at the head of the cavity, which is the shock regions. And a possible suggestion for the different spatial distribution is a different chemical origin. And in particular, SiO is believed to be formed directly from the release, from the sputtering of the dust grains, while SiS is believed to be formed via gas phase reaction. And if this is true, we can consider SiO as a tracers for shock regions. Since that moment, different works have been performed both in our research group and in different research group, with also some contribution presented in this conference a few years ago, in order to explain and try to understand the possible formation mechanisms for interstellar silicon sulfide, starting from gas phase reactions with simple precursors and, in particular, neutral-neutral reactions. Despite the huge effort and the different hypotheses and hypothetical mechanisms which has been proposed in order to form these interesting molecules, the two main astrochemical databases, namely the UMIS database and the KIDA database, which are the two databases used to model the chemistry of the interstellar medium, report as only reaction, or as most important reaction for the formation of SiS, the electron-ion recombination starting from the H-SiS plus cation. But the main problem is that this reaction, together with the reactions which are believed to be the formation mechanism of the H-SiS plus cations, have been found to be inefficient in laboratory experiment. So we started a systematic investigation of reactions involving silicon and sulfur in order to try to have different formation mechanisms for SiS, involving both ion-neutral reaction, but also neutral-neutral reactions. In this work, we study the reaction of the sulfur cation in its ground state with the SiH2 radical. These are two extremely reactive species, and in particular, the SiH2 radical is believed to be formed starting from the SiH4 precursors, which is believed to be abundant through photodissociation or other high energetic phenomena. The reaction leads to the formation of two different cationic isomers containing both silicon and sulfur. And then we started to investigate also the possible proton transfer mechanism driven by an ammonia molecule in order to have information for the formation of the neutral silicon sulfide molecule. For this purpose, we performed a theoretical investigation through electronic structure calculation using, for the first analysis, the density functional theory with the Betrelip hybrid functional and the triple zeta plus polarization and diffuse function basis set to perform geometry optimization of all the stationary points and vibrational frequency calculations to assess the nature of each stationary point. With this framework, we derived a first version of the potential energy surface, and then we refined the energy of the different stationary points with the more accurate coupled cluster theory with the same basis set. And we obtained the potential energy surface for the two reactions. As we can see in this slide, the reaction between the sulfur plus cation and the SiH2 radical start with the barrierless interaction of the two fragments, leading to the formation of an intermediate, mean one, whose global exothermicity is around 281 kJ per mole, and it's characterized by the formation of a new SiS chemical bond. Once formed, this intermediate can directly undergo hydrogen elimination, leading to the formation of the HSIS plus cation in a barrierless process, or it can isomerize through the transition state TS1, which is characterized by the transfer of an hydrogen atom from the silicon side to the sulfur side of the molecule. In this way, we can form the intermediate mean 2, which is a bit less stable than the first intermediate mean 1. And from this point, we can form both the cationic isomers through the elimination, depending on whether the hydrogen is eliminated from the silicon side or the sulfur side of the intermediate. One last possible process is a further isomerization in which the second hydrogen atom is transferred from the silicon to the sulfur, leading to the formation of the minimum mean 3, which is characterized by the presence of an SH2 group. And also in this case, we can have the fission of an SH bond, leading to the formation of the SiSH plus cation, together, of course, with atomic hydrogen. It's interesting to notice how the elimination of atomic hydrogen from the silicon side is barrierless in all the cases, while the fission of the SH bond is characterized by the presence of a transition state. But most important is that the reactions does not show an entrance barrier, and all the stationary points lie below the energy of the reactant. So in principle, considering the energy, this reaction is feasible also in the regions of the interstellar medium where the temperature and particle density are extremely low. Once the two isomeric cations are formed, we follow the idea of Charney and co-workers who analyzed the high abundance and proton affinity of ammonia and suggested this molecule as good partner for proton transfer process. So we adopted the same strategy to perform a theoretical investigation of the two proton transfer processes, starting from both the different cations. And we found also in this case that the two processes are barrierless and exothermic. They are characterized by they are characterized by stationary points which are extremely exothermic. And each potential energy surface shows only one minimum, one intermediate, in which the ammonia molecule interact with the hydrogen side of the cation, leading to the formation of the NH4 plus cation and neutral silicon sulfide. Now, the main issue with this system is that, as we can see also from the previous potential energy surface, the multiplicity of the sulfur plus cation in its ground state is 4, which means that all the stationary point, all the intermediates in the potential energy surface has a global multiplicity of 4. And according to the selection rules, we can form the two cationic isomers only in its triplet state, which means that the subsequent proton transfer process will lead to the formation of silicon sulfide in its triplet state, which is the first electronically excited state. So in order to investigate the possible formation of silicon sulfide in its ground state, what we are doing in this moment is try to invoke the intersystem crossing, which is a non-adiabatic transition between two potential energy surfaces with different spin multiplicity. And in this way, we will allow to reach the doublet potential energy surface generated by the reaction of the SiH2 radical with S plus in its doublet D state. And in this case, we will lead to the formation of the two ions, the two cations, in its singlet state, and the subsequent proton transfer process will lead to the formation of silicon sulfide in its ground state. We plan also to perform a kinetic investigation in order to derive the rate constant and the product branching ratios for the reaction. And in particular, we want to use a new approach with respect to the previous cases, which allow us to analyze the capture process, so the initial bimolecular approach, with a semi-empirical model, and in particular the improved Lennard-Jones potential, to obtain the energetic of the process, which will then be used with the capture model to obtain the rate constant for the initial channel, and then the RRKM theory for all the unimolecular process of the composition of the intermediate. This will allow us to obtain the rate constant and the product branching fraction. But of course, we need to deeply investigate the full potential energy surface, including all the possible minima, transition state, and product, both from the 4 PAS and from the doublet potential energy surface. So in conclusion, we can say that we investigated new possible formation mechanisms for interstellar silicon sulfide involving gas phase ion neutral reaction, and starting from precursors which are simple and extremely reactive, and which are already observed in the same shock regions in which the two SiO and SiS molecules have been detected at the beginning. As I said before, we need to invoke the intersystem crossing in order to deeply understand and consider the formation of SiS in its ground state. So the future perspective, together with a complete investigation of the potential energy surface, are a kinetic analysis to derive the rate constant and branching fractions, in order to include this new data in the astrochemical model and to see if the tidal reactions can be considered possible and valid alternative for the formation of silicon sulfide in the interstellar medium and improve the astrochemical databases. So I think I can stop here, and thank you all for your attention.
Thank you, Luca, for this nice talk. So now here is opening for the discussion, some questions. At home, for the virtual participants, some questions. I have a curiosity, Luca. So you are presented this reaction because it's important in the interstellar medium. So you compare your results with some, say, the experimental results or astronomical results?
Well, we have the astronomical results of the observations.
Okay.
The one I presented is one, but I think, well, there are observations in different regions of the interstellar medium. The problem with the experimental investigation is that this kind of reactions involves transient species, which are also difficult to generate in a controlled manner in a laboratory experiment. And this is the reason why usually we only have theoretical prediction for this kind of reactions.
Okay, thank you.
Thank you.
Some more questions? Curiosities? Okay, thank you, Luke, again.
Thank you.
And thanks all the speakers of this session. And we have finished with this session, and we move to the coffee break, I think so. Okay, thank you again.
So I think that we can start this afternoon session. We are a little bit late actually. And the first presentation of this section, which is part of the Compastro workshop, is done by Luca Mancini, and he will present a work titled A Theoretical Investigation of the Reactions of Nitrogen, WT, and CN with acrylonitrile and implications for the prebiotic chemistry of Titan. Luca, you can, Luca, you can upload your presentation.
Okay.
And when you are ready, you can start.
I hope now you can see.
Yes.
Okay.
Okay, perfect. You can start when you want.
Okay, thank you for the introduction. In this talk, I will try to focus the attention on gas phase neutral-neutral reactions, but which are important in a different astronomical field, which is the field of planetary atmospheres, and in particular, the prebiotic chemistry of Titan. So first of all, I'd like to underline why we are so interested in Titan. Titan is Saturn's largest moon. It's the second largest moon in our solar system, but its peculiarity is that this is the only body in the solar system, with the exception of our planet, to have a thick atmosphere mainly composed by molecular nitrogen, which accounts for around 95 to 98%, with the remaining part being methane with small tracers of other carbon-rich compounds. And the interest in this body is indeed because of its atmosphere and because of its similarities with our planet, considering also the fact that the appearance of life on Earth drastically changed the properties of our planet. So in order to try to understand the first evolutionary stages of our own planet, we have to look at other bodies in the solar system which share some similarities. And the best candidate for this purpose is Titan. Considering its distance from the Sun, the temperature on Titan is very low. At the surface, we have a temperature of around 94 Kelvin, which means that all the water is present as water ice, and there are liquids like rivers, lakes, and a liquid cycle, which can be similar also to our water cycle on Earth, made of methane and some traces of ethane. According to a last model, the structure of Titan is composed by 5 major layers, including an inner layer of water-bearing silicate rocks, 2 layers of water ice, with in between salty liquid waters, and the whole surface is covered by an organic haze, which is made of carbon-rich molecules also containing nitrogen atom, which gives to Titan its peculiar orange color, which has been seen also from the different missions, including the Cassini missions, which was able to reach the surface of this body and gave us a lot of information about Titan's surface, but also atmosphere. In this talk, I will focus on the reaction between a target neutral molecule, a closed shell molecule, which is acrylonitrile, which can be seen as an ethylene molecule with a CN group replacing an hydrogen atom, with 2 different reactive species, the CN radical and atomic nitrogen in its first excited state. We look at the first excited state, the doublet D state of atomic nitrogen, simply because the ground state, the 4s state, is not reactive, and it's easily interconverted in the doublet D state. Both the reactive species can be easily formed via photodissociation of simple precursors like molecular nitrogen and HCN. And the target molecule, acrylonitrile, is particularly important. It's been detected in Titan's atmosphere, both from ground-based observation with the ALMA telescopes and from space missions, but it's particularly important because it's considered the perfect candidate for the formation of membrane-like structures in a non-aqueous environment, such as the liquid methane, which is peculiar on Titan. If we look at the abundance of acrylonitrile as a function of the altitude, we can see a peak in its mole fraction at around 1,000, 1,100 kilometers, which is the upper atmosphere of Titan, in which the temperature is around 175 Kelvin. At the same altitude, both the reactive species, atomic nitrogen and CN, show a peak, show a high abundance. So in principle, by considering the abundances, these two reactions are feasible in the upper atmosphere of Titan. For this reason, we started a theoretical investigation of the two reactions via electronic structure calculations. A first analysis was performed using density functional theory with the Beatrice hybrid functional and the triple zeta plus polarization plus diffuse function basis set. We performed geometry optimization for all the stationary points, followed by harmonic vibrational frequency calculations in order to assign the nature of each stationary point. And we performed also IRC, intrinsic reaction coordinate calculations, to properly assess each stationary point linked with the correspective reactant and products. With this approach, we obtained the potential energy surface for the two reactions. These are the results for the reaction of the CN radical with acrylonitrile. As we can see, the first step of the reaction is the attack of the carbon side of the CN to the CH2 part, to the carbon atom of the CH2 group of the acrylonitrile molecule, leading to the formation of two possible intermediates, min1 and min2, depending on the orientation of the attack of the CN radical. These two intermediates can be easily interconverted by overcoming a very small barrier characterized by the rotation around the carbon-carbon bond of the structure of the intermediate, which shows a partial double bond character. Both the intermediate can undergo hydrogen elimination. A saddle point has been identified for both cases, which means that an energy barrier must be overcome in order to form atomic hydrogen together with the related cofragment, which is an isomer, which contains two CN groups in the structure. Also, in this case, the orientation depends on the orientation of the initial attack. The reaction in this case is barrierless, and all the stationary points lie below the energy of the reactant. So in principle, by considering the energy, this reaction is feasible, also considering the low temperatures of Titan's atmosphere. The same approach has been used for the reaction of atomic nitrogen. In this case, the potential energy surface appeared to be a bit more congested, and the stationary points are characterized by higher values of exothermicity, and this is mainly due to the fact that being atomic nitrogen in its first excited state, it carries out a higher quantity of energy, so the intermediates are formed with a higher amount of energy. In this case, the first step of the reaction is barrierless and is the attack of the atomic nitrogen to the carbon-carbon double bond of the acrylonitrile molecule, leading to the formation of the min1 intermediate, which is characterized by the presence of a three-member ring carbon-nitrogen-carbon. The global exothermicity of the process is around 444 kJ per mole, and once formed, this intermediate can undergo hydrogen elimination, and in particular, it can form two different isomers. Also, the product isomers are characterized by the cyclic structure, CNC structure. Two different isomers depending on whether the hydrogen is eliminated from the CH2 side of the intermediate or from the CHCN side of the intermediate. Alternatively, we can have the breaking of the carbon-carbon bond in min1, leading to the formation of min4. And also in this case, two different isomers can be formed by the fission of the carbon-hydrogen bond. In these cases, the two transition states identified, TS7 and TS8, we can see that they have a value of energy which is the same as the energy of the product, also justified by the fact that the bond length between the hydrogen which is eliminated and the related carbon is higher than 2 or 3 angstroms. So we included the transition state to have a general overview of the potential energy surface, but from an energetic point of view, we don't think that they will affect so much the reaction. Additionally, one last process is possible starting from min1, and it starts with the transfer of a hydrogen atom from the carbon to the nitrogen atom of the structure, leading to the formation of the min3 intermediate, and a subsequent carbon-nitrogen bond breaking lead to the formation of min2. This intermediate has an linear structure in the sense that it's not characterized by the presence of the initial ring, and it's characterized by the insertion of the atomic nitrogen in the carbon-hydrogen bond. And also in this case, it can lose a hydrogen atom, leading to the formation of atomic hydrogen and the related cofragment. So these are the two potential energies that we obtain in a first DFT analysis. So the future perspective are also in this case a complete evaluation of the potential energy surface, also using the couple cluster approach in order to obtain more accurate energy values. We recently employed this method that I showed to complete the analysis of the CN radical with the acrylonitrile molecule. We investigated the possible attack of the CN also through the nitrogen side, and we found that all the barriers, the transition state in the potential energy surface, lie under the energy of the reactant. So the process is believed to be not very efficient under the low temperature conditions of Titan. The only possible process will be the isomerization, leading to the formation of a minimum which is common between the two potential energy surfaces. So this will allow to reach again the potential energy surface related to the carbon, to the attack through the carbon side, and the formation of the previous explained products. We coupled the electronic structure calculation analysis with a kinetic analysis, which allowed us to derive the rate constant and the branching fraction for all the channels. And also in this case, we adopted a new approach using the semi-empirical potential to model the initial attack of the two fragments. And with this framework, we obtain values of rate constant which are more in line with the values obtained by previous experimental investigation, even though they are at high temperature for this system. We coupled the theoretical analysis with an experimental investigation performed in our laboratory in Perugia through the cross-molecular beam techniques, which allow to investigate the reaction under single collision conditions and to study the single reactive event. In this case, we can see a very good agreement between the theoretical prediction and the experimental data, which detected only atomic hydrogen with different possible cofragments as product of the reaction as predicted by the theoretical calculations. The same approach is employed also for the reaction of atomic nitrogen with acrylonitrile. In this case, the potential energy surface is more complex. We have more than 20 possible intermediate with all the related transition state and all the possible products. But first, kinetic analysis allowed us to derive the branching fraction, so to identify which are the most important products, and we found that the products which are formed with an high percentage, so which are most probably formed, are related to, also in this case, hydrogen elimination process starting from the first intermediate min1, which is the intermediate characterized by the three-member ring, and from the linear structure obtained by the breaking of the carbon-carbon bond. So also in this case, we have only atomic hydrogen as possible product of the reaction together with the related cofragments. And this data can be analyzed also on the basis of the data obtained in the lab. And also in this case, we have a very good agreement between theory and experiments. So to conclude, we performed a new theoretical investigation of the two reactions between acrylonitrile and two reactive species, CN and nitrogen, and we found two different mechanisms for the initial attack. In particular, the CN attack the carbon atom of the acrylonitrile molecule, leading to the formation of a new carbon-carbon bond, while the atomic nitrogen attacked the double bond of the molecule, leading to the formation of a cyclic intermediate. We refined the energy at the couple cluster level to have more accurate value of energy for the full potential energy surface. We compared the data with the cross-molecular beam experiment, and in this way we were able to derive the reaction mechanism. So the next step is basically the inclusion of the data in the photochemical models of Titan atmosphere, also considering the fact that previous data were inserted for the reaction of CN with acrylonitrile, considering data which were available only at high temperature, so they were extrapolated at low temperature, while for the reaction of atomic nitrogen with acrylonitrile, there were data based on analogies with similar system. So with this work, we aim to give new data to improve the photochemical models in order to properly model the abundance of acrylonitrile, considering new possible destruction mechanism. This was my last slide. I thank you all for your attention.
Thank you, Luca, for this nice presentation. We have time now for questions, curiosities. Also online, of course, you can make any observations you want. I have just one curiosity. You said before that for the reaction between CN and acrylonitrile, in the initial step, you used a semi-empirical potential. Can you say something about this potential, which kind of problems?
Yeah.
Did you hear me?
No, sorry, I lost the connection for a moment.
Okay, perfect. Okay, and I was just saying that you talk about the initial step of CN plus acrylonitrile, and you said that you used a semi-empirical potential.
Yeah.
Can you say something about that? Which kind of potential did you employ?
Okay, yeah. So usually in our kinetic analysis, we employ the capture theory. So we basically perform the electronic structure calculation by fixing the distance between the two interacting fragments, and we use that energy to perform capture theory calculations to derive the rate constant for the initial attack. In this case, we used a semi-empirical potential, which is the improved Lennard-Jones potential, which has been developed in our university a few years ago, which is a semi-empirical potential which is composed by attractive and a repulsive part. So it allows, as a function of the distance, including also the electrostatic part, to derive the energy, the potential for the initial attack as a function of the distance. And then we use that to run the capture theory calculations to derive the rate constant.
Okay, thank you, Luca. That's very clear. There are other questions? Okay, thanks again, Luca, and we can move to the next speaker of the session, which is Ariasno Kakar. Ariasno?
It's no.
No?
Yeah.
Okay, perfect. Yes. Presentation. And Ariasno will present a contribution titled an ab initio computational study of binding energies of interstellar complex organic molecules on crystalline water ice surface models. So you can start when you want.
Thank you.
It's yours.
Okay. So, good evening. I am Harjas Noor from the Autonomous University of Barcelona, and today I'm going to present a computational study of binding energies of ICOMs on crystalline water ice surfaces. Before going into my work, I would like to give a brief overview about the stellar systems and their evolution. So we start in the pre-stellar phase where there are diffuse clouds of dust particles and gaseous molecules which condense to form cold and dense molecular clouds. And from there, it evolves through various stages to finally reach a solar type planetary system, such as the one that we live in. Along with the stellar evolution, the chemical evolution also takes place from simple molecules such as water to biopolymers in the last stages of the evolution. So what is the interstellar medium? It is the region between the stars which, well, might seem empty, but it's not. It's actually composed of matter such as dust particles and gaseous molecules, and also radiation. In the pre-stellar phase, the molecular clouds that are cold and dense molecular clouds exist, which are the nurseries for the birth of stars and their planet systems. The molecular cloud gravitationally collapses in upon itself to form a gaseous clump and an envelope around it, which is called the protostellar phase. The core of this protostar heats up to about 100 Kelvin compared to the previous 10 Kelvin in the prestellar phase. This increase in temperature leads to the overcoming of energy barrier, and hence we can see the formation of more complex molecules in this phase. The envelope around the protostar then evolves into a protoplanetary disk in which more than 99% of the mass is condensed at the center, while the remaining 1% is what forms planets and asteroids and comets around this newly formed star. The protoplanetary disk is optically thick, so it is hard to detect what molecules are present in this phase. But well, we can speculate that it has remnants of both prestellar and protostellar phase molecules. Well, in the prestellar phase, the temperature is around 10 Kelvin, so the gaseous molecules, they freeze out onto the dust grains. The dust grains are submicron particles made of carbon or silicates, while the ices that cover the dust grains are composed mainly of water, but also other molecules such as carbon monoxide, carbon dioxide, ammonia, methane, and methanol. The grain mantles provide a surface for the adsorption of these species, where they can diffuse to interact with the other molecules. They can react to form products, and then these products in the protostellar phase, due to the higher temperatures, they can sublimate into space where we can detect these molecules using rotational spectroscopy. The processes that occur on the grain surfaces can be astrochemically modeled. And here you can see the rate constants, where binding energy is an important parameter of these expressions. Therefore, it is really important to obtain accurate binding energy values in order to account for the mechanisms of these processes. So what's the big deal with ICOMs? Up to now, nearly 270 molecules have been detected in the interstellar medium, out of which around 40% of these molecules are interstellar complex organic molecules. That are the molecules which contain more than 6 atoms and have to include at least 1 carbon atom. Now, the molecules such as ethanol or acetic acid might be simple in Earth's terms, but in the interstellar medium, the formation of these molecules is quite complex. It is really important to understand the formation of these molecules because they are the building blocks of biologically important species. In this work, I have computed the binding energies for these 13 ICOMs on crystalline ice, where I have used a unit cell made of 24 water molecules, along with periodic boundary conditions so as to simulate the whole ice surface. Although amorphous ice would be more realistic in the interstellar medium, but simulating the amorphous ice surface would require a bigger unit cell, and therefore it is computationally more expensive. So we start with the crystalline ice. The binding energies have been calculated using density functional theory. The method that we use is B3-lip with D3 dispersion correction and Becky-Johnson damping. The binding energies have been divided into 2 groups. The first is the hydrogen bond donors and acceptors. In this group, the adsorbate is forming multiple hydrogen bonds with the ice surface. Therefore, the hydrogen bond cooperativity is higher in this group compared to the only hydrogen bond acceptors, where the adsorbate forms only 1 hydrogen bond with the surface. So naturally, the binding energy is higher for the first group. An advantage of this method is that it gives us the dispersion and non-dispersion contribution to the binding energy separately. Therefore, we can get the percentage contribution of the dispersion interaction to the total binding energy. So we can see that the species that only form or that are only hydrogen bond acceptors have a higher dispersion percentage compared to the first group. This is again because in the first group, the non-dispersion interaction, that is the hydrogen bonding, is much higher as compared to dispersion. I have compared the values that I obtained in this work with the previously reported literature values. So we can see that the binding energies in this work are higher than the previous 2 works. This is because, well, in the first work that I took, they used a GGA functional to compute the binding energies, which lacks the dispersion correction. Therefore, they were losing out on almost 40 to 50% of the binding energy. In another work, they took the dispersion correction into account, but the model that they used to simulate the ice surface, it was different. They only used 1 single water molecule for the ice surface simulation. Therefore, they neglected the hydrogen bond cooperativity that is the non-dispersion interactions. Along with the DFT calculations, I also checked the CCSDT correlations. So my system is composed of 80 atoms, therefore it is impossible to use the couple cluster method on the whole system. So we used an onium-like approximation where we take a model which is composed of the adsorbate and the closest water molecules that are directly interacting with the adsorbate. We calculate the binding energy for this model using CCSDT, while we compute the binding energy for the whole system using B3-lip, the DFT functional. Up to now, this work has been carried out on the crystalline ice surface, but the objective of this whole work is to obtain accurate binding energies in the interstellar medium conditions. Therefore, we need to use the ice surface in the amorphous state. But modeling the amorphous ice would require a bigger unit cell in order to account for the long range order, the lack of long range order, and the various binding sites. And hence, we need a cheaper but almost equally accurate method to calculate the bindings. Here we propose a hybrid methodology, which is the DFT-HF3C, where we compute where we optimize the structures at HF3C, which is a lower level of theory. And then on the optimized structures, we perform single point energy calculations using the B3LibD3. So we first tried this method on the crystalline ice in order to test how it compares with the full DFT treatment. So we take the HF3C and we optimize these molecules using we optimize the whole structures using HF3C, where the 3C stands for the 3 corrections for basis set superposition error, the dispersion interactions, and also errors that are introduced due to using the minimal basis set. And then after obtaining the optimized geometries, we perform the binding energy calculation using B3LibD3. Here we can see that the correlation is quite well between the full DFT and the DFT-HF3C method. So this cost-effective hybrid method can be used to compute the binding energies on the bigger realistic amorphous ices. To conclude, well, the DFT functional that we take, B3LibD3, it provides accurate binding energy values in our case. The binding energies of the hydrogen bond donors and acceptors are higher because of the higher hydrogen bond cooperativity in this group. Dispersion is a major contributor to the binding energies. Therefore, we need to make sure that we use a functional that includes the dispersion interactions. The most important takeaway would be that cost-effective DFT-HF3C is a robust approach to obtain accurate binding energies, and it can be used to compute binding energies on the larger amorphous ice surfaces. I would like to acknowledge the Quantum Grain Group and the UAB, and also ERC for the grant. Thank you.
Thank you, Alex, for this presentation. Now we have time for questions, curiosities, of course also online. I have just a curiosity. I noticed that you use for bit-to-lip calculations the D3 dispersion scheme. Did you try also to use other dispersion schemes? Or?
I did not, because in our group they have already used this this B3LibD3 method, and it gave really accurate values. So we did not try any other method. Yes.
So the previous calculation show you that
yes,
that's the best
right.
method for in order to compute dispersion.
Yes.
Okay, thank you. Any other question? Okay, thank you again, Ayasno. And we can move now to the next speaker, which is Marco Pariani from the University of Perugia, and which will present study titled Stereodynamics of Autoionization Reactions Induced by neon star metastable atoms with hydrogen chloride and hydrogen bromide molecules. Experimental and theoretical study of their activity through selective collisional angular course. Okay, so Marco, you can start.
Okay.
Yeah, as Professor Rossi said, our research is focused on auto-ionization reactions, in particular involving neon star metastable atoms as ionizing agent on hydrogen chloride and hydrogen bromide molecules. This investigation was carried out with both theoretical and experimental approach, and we chose the hydrogen bromide not randomly, but starting from previous determinations on hydrogen chloride ionization. A few words about auto-ionization reactions before going through the specific ones. They are described as elementary gas phase reactions in which neutral reagents are able to generate more stable ionic species. They are most important in ionized part of the atmosphere, the ionosphere. And they are relevant in combustion chemistry, plasma physics, and as well in astrochemistry, like the lack of oxygen in the ionosphere of Mars has been described thanks to a Colombian explosion next to auto-ionization. We will refer in this work to collisional auto-ionizations or pending ionizations because we will have a reagent species in an internally excited metastable state as an ionizing agent. In our case, it will be the noble gas. The pending ionization has been demonstrated by our research group that can be described with a semi-empirical models to rationalize it as an elementary oxidation process in a specific thermal condition, as it's schematized in the equation, in which you can recognize the noble gas open shell atom in an electronically excited metastable state, and the target molecule is the X molecule. We can highlight the process that generate a collision complex in an excited energetic state, and which relaxes through an electric emission. For such reaction, the complex is not only the precursor state, but also the transition state, which gives rise to the products of the reaction, which can be the ionic products, as well as the dissociated or rearranged ions. In specific thermal conditions, this occurs by an oxidation process and is highlighted in the equation by the left-going arrow, representing an electron exchange between the target X and the noble gas. In this article, in this work, we report mass spectrometric determinations as a function of the collision energy in the range of 0.03, 0.5 electron volt. We performed this study using a cross-molecular beam apparatus, which permits us to measure the total and partial cross sections for the all open ionization channels.
Sorry, the screen doesn't appear. It's locked on YouTube. So you can continue.
Okay. As I said before, we didn't choose bromide molecules randomly, but we did the previous mass determinations on hydrogen chloride system, which showed the formation of the following ionization channels at an average collision energy of 45 millielectron volt. And you can see that there be relative abundance of the specific channels. We did both the investigation both from the theoretical and the computational way. And our theoretical approach is founded on the so-called optical potential model introduced in 1940 by Hans Bethe. And the slightly different is slightly different our semi-classical treatment, but it's based on OPM, on the classic OPM, in which a complex potential can describe the intermolecular microscopic autoionization dynamics. Specifically, is composed of two parts, one real part, which is V, and one imaginary function that can be used for describe the probability through which the intermediate conditional complex evolves toward the formation of the products. And our group developed a new semi-classical treatment based on the OPM, in which the two functions are treated like interdependent analytical functions. Through that, we clarified that the autoionization reactions can be prototype of simple oxidation processes in a specific thermal condition. In fact, we can distinguish between an indirect mechanism and a direct mechanism. The indirect mechanism is the classic one, a typical photoionization through a physical mechanism, which happens at low energy collision. For what concerns the direct mechanism, when we reach the thermal or hyperthermal regime, we can investigate a real oxidation mechanism, so a chemical mechanism that became prominent through an electron transfer between the ionizing agent and the target molecule X. We describe here the cross-section measurement apparatus, which is coupled to a mass spectrometric technique. We have this apparatus in Perugia, and is formed by three chambers, pumped by they are pumped vacuum chambers, in which the pressure goes from 10-7 to 10-5 to 10-7 in the detection chambers, in the third chamber, and is schematized in this slide. We have the primary chamber, in which the rare gas metastable atoms are generated through a microwave discharge and an electron bombardment at around 150 electron volt. The second chamber, in which the primary beam of atoms is analyzed in its velocity through a TOF technique, a time of flight technique. And the third chamber, that is the scattering one, which hosts the cross-molecular beams volume and the two diagnostic devices, which allows the detection of product ions and the kinetic energy of the electrons that are emitted. The performed analysis, the performed determinations show the opening of the relative channels relative to the HBr molecules, and we can see the relative abundances for each open ionization channels. And we determined in the range of 30-500 millielectron volt the formation of the associative ionization products, the pending ions, and also the products of proton transfer reaction, but with a relative abundance under the 1%. If we compare the total ionization cross sections for chloride and bromide molecules, you can see some trends. We can see that for HCl, we have a global, more efficient ionization process in the whole range of the probe collision energies. In fact, if we focus on the ionization cross section at 100 millielectron volt, we have double the value in angstrom for the neon star HCl system respect to the HBr system. If we compare the relative abundances of the open ionization channels, we can notice a higher efficiency to react following a proton transfer reaction for the HCl respect to the HBr. This sadly led to the impossibility of comparing the ionization branching ratios for this kind of reaction because of the low abundance of the ionization channel relative to the HBr. The other channels showed a relative probability of the associative ionization quite similar for the two systems. If we go back to the total ionization cross sections, we have a faster decrease of the neon HCl plus formation for collisional energies higher than 45 millielectron volt respect to the one with HBr. And we have a decreasing trend in general as the collisional energy increases for both systems, as we can see in the total ionization cross sections. We can discuss the two mechanisms also through this open channel, these open ionization channels. We have open channels which are forming different electronic states of the product ions, and they are promoted by specific angular cones within which the reaction takes place, with spatial acceptance and defined orientation. We have the indirect mechanism, as we said, the classic mechanism, physical mechanism, in which we have a collinear approach, a H-end collinear approach of neon star to the HX. Instead, and this interaction is characterized by a mixing of atomic orbitals with different symmetry. And that's one reason that stimulates this mechanism. Instead, the direct mechanism, in the direct mechanism, we have an approach, a different approach. Neon star and the partners, the target molecules, are approaching along the collinear direction, with neon star not towards the hydrogen, but towards the X atom target, so towards bromide or chloride. And this mechanism became an oxidation. In this kind of mechanism, the target molecules behaves like a reducing agent, and the behavior of neon star is dominated by its ionic core. In conclusion, we have discussed the total and partial ionization cross sections for the reaction of neon star that induces autoionization on HCl and HBr molecules. And we distinguished between two different microscopic mechanisms. And they are dependent on the stereodynamics of the open ionization channels. And they clearly show different orientation and acceptance, which leads to the different physical and chemical mechanism. Furthermore, there is also there are more reasons because of this behavior, and we can nominate the polarization effects. We have clearly HBr and HCl that are similar molecules, but HBr molecule is less polar than chlorhydric acid. So the polarization effects on neon are attenuated for the HBr molecule. And also the overlap integral between the orbitals of the colliding partners. That's because the molecular orbitals of bromide acid are more diffuse with respect to those of HCl. And in conclusion, also thanks to the so-called sigma hole, which is localized along HX bond length on the external X part of the target molecules. The effect of this sigma hole is increased when the target molecules is the bromide. Thank you for your attention.
Thank you, Marco, for the nice presentation. So time for questions or observation. I want to know do you plan to apply the same procedure to other systems to study different systems with respect to the one?
That can be an interest topic because clearly we have we know very well halogen systems, so they can be an example to study different systems, because this mechanism can be common also to other species, and also it can be interesting also to investigate the other halogen atoms like fluorine and iodine, because it's not so simple that they have this trend of efficiency in ionization, because, for example, ionization potential for HBr is less than the one for HCl, but the efficiency is higher for HCl. So it's not a so simple trend to describe. So it could be interesting, yes.
Okay, thank you, Mark. Okay, so we can move to the last speaker of this session, which is online, and is Lydia Ayai, which should be connected.
I'm connected. Good afternoon. Good evening. I'm connected. Yes.
You can turn on your camera, Lydia, and you can open your microphone.
Lydia, sorry, we hear you very low.
Oh, really?
Please go near to the microphone and turn your camera, please.
Okay. Good evening.
Yeah, but we hear you very, 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 very low.
Oh, okay. I will try to. Can you hear me now, sir?
Yeah, better.
Sorry, can you give me a minute?
Try also to share the screen, because we cannot see
your presentation.
We cannot see your presentation. Okay. And try also to speak loud, because it's very difficult to hear you. So try to share your presentation first. Yeah, we can see now the presentation, but it's almost impossible to hear you. I don't know, try to speak loud.
Can I talk now?
Yes. Yeah, we can hear you better than before. Okay.
Okay.
Okay, so next presentation is by Lydia Ayai, which will present a paper titled Acoustic Nudging Based Model for Vocabulary Reformulation in Continuous Yoruba Speech Recognition. You can start, Lydia, when you want.
Okay. Good evening. My name is Dr. Hajayi Lydia Kende. And my topic is Acoustic Nudging Based Model for Vocabulary Reformulation in Continuous Yoruba Speech Recognition. And these are my presentation offline. We have the introduction, related work.
Lydia, sorry, can you put in full screen mode your presentation? It's better.
Okay.
On the bottom near, it's next to the zoom options. There's presentation mode. If you push it, we can see you better, the presentation.
Okay.
Lydia, don't worry, don't worry. Don't worry, it's okay, it's okay. You can continue with your presentation, don't worry. Continue
Okay.
on this way, it's no problem.
Okay. So these are the presentation outline: introduction, related work, the acoustic nudging model, result and discussion, and conclusion and future work. Speech is one of the most inconvenient means of communicating between people and humans. And for this module, we are making use of Yoruba language, which is spoken in Nigeria, which is an indigenous language, having the largest ethnic group in Nigeria, spoken with about more than 50 million people, and about 30 million speaks standard Yoruba language. And at the same time, Yoruba language falls under low resource language, which are languages that has low input on the internet. And several efforts have been made to develop interactive system to realize both the voice and the speech synthesis. And we also have different classification of automatic speech recognition, which are isolated, continuous, spontaneous, and connected. And the focus of this study is actually on continuous. Back to the literature review. Someone designed HMM-based timing speech recognition, but has low accuracy. Another one developed a GMM-based isolated using MATLAB, but had about 70% accuracy. And at the same time, a mobile tourist assistant designed a Yoruba language ASR for tourists on Android application and had about 85% clarity. Same thing with PhonePe with about 71.07%. So all these existing studies have no consideration for automatic correction of ASR errors involving user acoustic. So this our study is going to propose acoustic nudging model in order to reduce word error rate and sentence error rates compared to existing model. Talking about the acoustic nudging, which is our model, it's a concept that is derived from behavioral science, which involves automatic reformulation of user acoustic irrational behavior, involving tracking, monitoring, detecting, and reformulation of user acoustic behavior in speech data. And this study is going to focus on large vocabulary, speaker dependence, and tone diacratized model. So this, and at the same time, this is our proposed acoustic nudging based model. There are different features. As I said before, that this study is looking into the continuous standard Yoruba speech to text engine. So we have different features that is embedded to make this a reality. And the first one is the feature extraction, which has to do with removal of noise from the speech data, then followed by different other. Also, we have the acoustic models, which is used as a statistical representation for our application to be able to recognize any user input. And the contribution to this study is the acoustic nudging model and the gesture mixture model. As I said before, that the acoustic nudging model is going to perform the automatic reformulation of speech recognition through tracking, monitoring, and at the same time reformulating speech data automatically. So another process we looked into is there are different processes that were engaged in development. We have the data collection requirement. For the data collection requirement, we made use of 47 standard Yoruba speaker, whereby we were able to collect their voices. And then after then, we tone diacratize the test. Since we have both the speech corpus and the text corpus, and to diacratize the test, we have to do that. We have to consider Yoruba language in order to increase the accuracy. the speech recognition. And we went through a semi-supervised standard Yoruba tone characterization process. And after then, we have the recorded speech signals. That's the data set we collected, as I said before, 47 different Yoruba speakers. We have the text corpus development, and then we were able to label the speech and the data. And at the same time, we made use of the feature extraction, that's the pre-processing, that's the removal of noise and silence, and then the acoustic reformulation and modeling, that's tracking of our speech data. And then you have the pronunciation dictionary. So after then, we went through 3 different processes. We have the training, the testing, and the validation. So for testing our ANGM model for the continuous standard Yoruba speech to test system, we had to form some results where we were able to gather 15 speakers consisting of both male and female adults. And then we gather about 2,300 speech files in order to test our application. And after then, we derived a mean accuracy of about 95.277. And for the word error rate in percentage, we had an average of about 4.723, which shows that our system is has a very high accuracy. And after then, we were able to compare our word error rate result for 15 different speakers, and these are the centers used. And we compare with other existing model. We have the GMM model, and we have the GMM HMM model. Our model has a lower error rate of about 4.091 compared to other models, from which can be visibly seen here. We had 4.091, which is very low compared to other models, showing that our application has an higher error rate. And this also shows an evidence for the above evaluation. So this is the WR comparison charts, and from here we can visibly see that our model has a very high accuracy level, which is very substantial. And at the same time, going back also, we had 95.237% compared to other models. We compared different models. We compared GMM, we compared GMM, HMM, we compared CNN and other models together. And then our model has a lower error rate. So in conclusion, after the development of our indigenous vocabulary continuous standard Yoruba speech to text reformulation (NG) for seamless communication, our system was evaluated using a word error rate of 4.723%. We derived 4.723% word error rate. So for the efficiency of the ANGM model, this study compared the performance of the ANGM model with other existing models in literature, either as a single model or hybrid model, using about 11 continuous standard Yoruba test data sets. And our ANGM model derived an average list mean of about 4.091 compared to other models which are listed here. And the average also was done using other models, which are also listed. We have 1.1%, 0.5%, 0.8%, and 1.4%. Also, our study was able to cater for the observed limitation of the existing speech domain, and through the development of a large vocabulary, CSYCS, compared as opposed to existing isolated Yoruba speech to text NG, with consideration for tone diacritization to increase accuracy, and then our acoustic nudging based decision mixture model. So this study is going to provide future research direction, which is going to include the design of a voice engine system for Yoruba accents, design of a voice engine for other African language, and the application of the ANGM model to various existing applications for enhanced accuracy and system performance. Thank you.
for your presentation. We have time for questions, observations. Okay, it seems that everything was clear, and so we have finished the session. Let's thanks again all the speakers of the session, and we can close the session.
Hello, can you hear me?
Lydia, the session is finished and we now are closing the session. Thank you. Bye.